Hello again, and welcome to the lecture 2.4, which is the last part of the second lecture. So let's look at the presentation. We will end now with a little bit more theoretical and general results. We have talked about conjugacy and examples of conjugacy and how that is useful in particular cases and also for prediction. And we will look at more uses of that and more examples of that later. But we can put that into a context because this is actually related to the exponential family of distributions. So it's not the exponential distribution, which is one particular distribution, but this is a family, the exponential family of distributions. So many parametric families of distributions can be written in a particular form. So it's written in this way. So you have the variable here. It can be one dimensional or several dimensional, and then you have the parameters here. And then you can write the density in this form. So there's one factor which only depends on x, there's another factor that only depends on the parameters eta, and then there's an exponential part, hence the name, where you have the eta vector dot product with a u function that is also a vector. So this is the core of the function. It can be written like this, and this is where eta and x interact. And then eta is called the natural parameters of the family. So in fact, many distributions can be rewritten in this way. And when they can, it's called an exponential family. So some examples of exponential families of distributions corresponding to particular choices of these G, H, and U. They are some normal distributions, beta distributions, Poisson distributions, gamma distributions, Bernoulli distributions, or binomial distributions for fixed n, multinomial distributions for fixed n, and many more. So there's lots of examples of this. And exponential families of distributions share many properties and can be studied together. So this is nice. So before we go on, let's just look at one particular example. Let me see. I will try to share the whiteboard instead. So let's look at the beta distribution. Then we have that the density is written like x given the parameters alpha and beta. And we know that this is written like 1 over b alpha beta. That was the beta function. X to the power of alpha minus 1. 1 minus x to the power of beta minus 1. So this is the definition of the density, and the question is this an exponential distribution, or is this an exponential family? So the question is then, can it be rewritten in this form? And in fact, you can just write this as 1 over b alpha beta, and then it needs to be some kind of exponential part here. So we write this as the exponent of alpha minus 1 times the logarithm of x plus beta minus 1 times the logarithm of 1 minus x. So this is just rewriting this whole thing. And in fact, now we can see that it has this formula. So it's a dot product. We could write it even more carefully. And we have a vector here which consists of alpha minus 1 and then beta minus 1. That's the eta vector, and then we have a dot product of log x and log 1 minus x. So in fact, this is an exponential family of distributions where this u function is equal to the vector log x and log 1 minus x. And the h function, that was the one that depended only on x, this is in fact equal to 1. There's no term corresponding to that. And then you have the last term, which is the parameter, only depending on the parameters. So g of eta is then equal to 1 over b of eta 1 plus 1, eta 2 plus 1. Because this is the function, and then we have the relationship between eta, basically eta is equal to alpha minus 1, beta minus 1. Okay, so it's just a rewriting, and you can do this with more or less effort with the other densities that I mentioned in the list. Let's go back to the presentation. One important property of exponential families is that they have conjugate priors, and in fact almost all examples that you have of conjugate priors are exponential families. So it corresponds very well to this issue of conjugacy. So just think about it. If you have a density that looks like this, so then you could define a density on the parameters with parameters nu and beta like this, which is just a sum power of g of eta times the exponential of eta times some parameter b. So now you can see that if the prior has this form and you multiply it with the likelihood, which has this form, then you can forget about this part here, which does not depend on eta. And then you get just an extra factor of g of eta, and then the exponential parts go together to form this part here. So you can see very smoothly that multiplying this and this gives you this, and it is in the same family. It's expressed just with the one parameter adding 1 and the other parameter adding this u of x function, where x is then the data, so it's fixed. So you have conjugacy. And as I said, except for some very special cases that are rather trivial, then this is also all conjugacies are on this form. So it's a nice way to study them. And you should also note that the conjugate family of priors is also an exponential family. So this, when you get these priors that you construct here, they are also in the same big family of exponential distributions. So this is nice. So exponential families of distributions have lots of properties. Not all of them are related to conjugacy. There are many other properties also. So, but just let's first mention that if you have a prior like this, and you have a number of observations, then you can easily write down the posterior. So this is then using the conjugacy in these families. But you have other properties also. For example, you have that, if x is this variable with this density, then u of x, this standardized function of x, its moments and expectations and further moments can be expressed by differentiation of this function here. So this is like a general formula. That means that it's for all exponential functions, it's rather easy to find the moments, at least, of this this function u of x. And further, for example, if you have a flat prior, then the posterior, so the flat prior would correspond to having, you know, nu equal to 0 and beta equal to 0. So then you would simply get this as the posterior. And then you can, from that, get lots of standardized results about the posterior, the maximum posterior, and so on. So these are nice things. We're not going to use them a lot in this course, but it's more for the interested student. And I'm just going to, I'm not going to prove this, I'm just going to end with a short proof of this statement. Okay, so back to the whiteboard. And let me see. I need to no, this is too slow. I should choose another whiteboard. Clear all drawings. That was right. Okay, so we want to compute the expectation. Draw. The expectation, no, sorry. Draw the expectation of x given eta of u of x. Now this can be written as u of x times the density of this x given its parameters, which we have now assumed is this exponential family form. So this can be written as, so g of eta can go on the outside. And then in fact, this can be written as the gradient over this eta of the following integral, h of x, the exponent of eta times u of x, dx. Now the reason for that, you can, if you take the gradient of this integral, you can move it inside the integral, and then you differentiate this exponential function, and the only thing that comes out of that is this extra u factor, which you have up there. So this is correct, and then you can write this as g of eta and the gradient of, now this is just a rewriting. You can write this as 1 over g of eta times the integral, and then you have g of eta hx exponent of eta times u of x dx. The only thing I've done here is to add this g here and here. And the reason for doing so is that this now gives you exactly the density that we are looking at, and integrating it over all possible values of x gives you 1. So this is then equal to g of eta, the gradient of eta of 1 over g of eta. And you can write this, in fact, as the gradient of eta times the logarithm of 1 over g of eta. If you think about it, that's really what this says. So you get minus the gradient of log of g of eta. Okay, so this was just some small computations at the end. We're not going to use this, but I thought it might be interesting for some. Okay, goodbye for now.